Each day, the United States burns 19 million barrels of oil. This is enough oil to fill 1,200 Olympic-sized swimming pools. This figure does not even include the amount of coal, natural gas, and other non-renewable energy sources being consumed. As we burn these resources, harmful gases such as carbon dioxide, carbon monoxide, and sulfur dioxide are released, damaging the atmosphere and creating air that is unsafe for breathing. I am Samuel Michaud, and my goal through work in the Kittelstedt Research Group is to help solve this issue through the use of strontium titanate, a semiconductor material known to convert water into hydrogen gas in the presence of light. My work on this project focuses on adding manganese to the strontium titanate particles. When thinking about how a photocatalyst works, it's useful to picture helping a friend move into a new apartment. You and your friend are on the ground, and he wants to put a few chairs on the roof of his apartment. With the first chair, you decide to just lift the chair as high as you can to get it on the roof. You eventually get the chair there, but you expend a lot of energy in the process. For the next chair, you decide that lifting the chair all the way to the roof was not your best idea. So you go out and you find a stepladder to help you get the chair to the roof more efficiently. A normal photocatalyst works similarly to the first scenario, where the chair represents the electrons in the photocatalysts. It takes a lot of energy to move the electrons from the ground state or valence band to the next energy level or conduction band, where the electrons can be used to create hydrogen gas from water. In most photocatalysts, this process is not efficient enough to be a useful method to produce energy. So scientists have found a way to add the stepladder to help the electrons move more efficiently in the system. This stepladder comes in the form of transition metal ions. These metals add a secondary energy level for electrons to move to, and from that level, the electrons can then move to the conduction band using less energy. The goal of my project is to look closer at how adding manganese into strontium titanate changes the properties of the particles. Although my work does not specifically look at the efficiency these particles have at converting water into hydrogen gas, discovering more about how manganese affects the particles will pave the way for future studies with this material. Knowledge of how manganese affects strontium titanate will also give insight into how alternative metals might affect the system, leading in the end to a more efficient energy production source.